Recorded is rolling. Welcome to Friday, May 6th. So, all right, 2 days over. Yeah, go ahead. Right, so, stats puzzles. You guys know last 2 days we've been looking at statistics, and the reason is that I want you guys to have a model of probability curves in your mind as we go into quantum mechanics next week. Right, so let me think. Right. Now, hang tight here because I'm going to look the rest of the agenda today. We're going to have probably about a good 15 minutes to into class today. I know it's been like a weird choppy week. Some of you guys have been out like here and there for testing. So if there's any day you missed, any materials you missed, it's probably not a whole lot to catch up on because we've just been having like really short days all this week. But we'll have some time at the end of class if you guys want to ask me any questions or can help each other out or just get caught up. If you finish what we get finished today, you want to pop it in the grade tray, you can do that, get some points. If you think you're a little bit behind, you want to check your stuff over the weekend and turn in Monday, then that is okay too. I'm talking about the stats page, right? The stats packet. Okay. And if you get if you're all up to speed and all your stuff is looking good and you are ready for the next class adventure, then that is on your desk. I put, you guys see this quantum mechanics journal, right? There should be one of these around just acting as a model. Now you should also have a big old stack of paper. You guys got a big old stack of copy paper somewhere on your desk? Right? And there should be a couple staplers going around. There's one over there with Max and Nick. And I've also got this red stapler right here. I'll pass that one around. All right, so if you staple together 4 sheets of paper, and then you can follow the model on your desk, and there you go, it goes like this. I've also uploaded a digital version of this to Google Classroom. If you want to just print that out, you can use that. Also, I will pass out to you guys a quarter page that has a whole list of topics on it. So that you can just like have a list of topics. So like number 1, how small is an atom? Number 1, how small is an atom? Oh yeah, nachos. Right? Right, so this is what we're going to be doing next week. So last thing we'll be doing in this, well, I've got another fun project for you guys after this, but so quantum mechanics, and then all we'll be doing is just keeping a journal, and I'll go topic by topic, just write a couple of notes per quadrant, or a couple diagrams, pictures, and then yeah, that'll close up the class. Okay, all right, now you guys are period 4, so guys, here's the deal about period 4. You guys remember this wacky schedule? All right, we still got 2 days of wacky schedule left. All right, now I'm not going to see you guys on Monday because there's testing in this classroom on Monday. Okay, so guys, on Monday, are you going to show up to this classroom?
No.
Oh, all right. Now, I've been working trying to figure out where you guys are going to go, and I got the answer this morning. They are out of teachers, out of subs. Well, for that matter, we're out of administrators and out of custodial staff and out of bus drivers. So you guys are going to be sent to, here, let me write this down so it's in writing. Outdoor dining. Okay, so outdoor dining. Okay. Right. Do you guys know where that is? Like the cafeteria, and there's that outside pavilion. Right. All right, so guys, on Monday, where are you guys going to go for 4th period, which is the first 3 hours in the morning? Where are you guys going to go? Outdoor dining. You guys all got that written down somewhere? Right. You guys can remember that? Okay, so that's the first thing. So the first 3 hours of next week. Yeah, so that's how that's working. Yeah, so normally I would kind of have something for you guys, but I was suspecting they would set you guys up with a teacher. That's not going to be the case. So do you guys have like a book to read or something to study for? I know there's exams coming up. You guys gonna figure out what to do with those 3 hours, right? So yeah, so sorry, can't really give you guys anything really structured because it's like a last minute thing, and there's who knows how you guys are gonna be supervised, how it's gonna work, but that's what we got. Yeah. All right, and then oh yeah, I'm starting to clean up my room because we're about to head towards the summer here. You guys see some zoetropes around on this desk? I'm gonna have to start tossing these, but if you have one that you really like or want to show your siblings or parents or friends, then yeah, start picking those up because I'm starting to clean up around this place. Okay, all right, you guys good with this checklist, what we're doing? All right, let's get to this stats puzzles. Right, so real quick recap we've been doing so far. We've been looking at these bell curve distributions, and I've been using examples of heights and also like volume of water at some point. Okay, there's we've been making mostly two measurements for a whole population of data. We're looking at what's the average, like the mean average, right? Which hopefully you guys have been able to do for years, right? Just add up all the numbers and divide by the number in a group, right? And also something that might be new for you guys is standard deviation, which is a measure of spread, right? And what it means on this bell curve, right? And it's just past couple of days, but we're doing a recap here, right? You guys see this bell curve, how like the middle part of it looks like an upside down bowl, but the tails look like a part of like a right side up bowl. Where it switches is a point called the inflection point, and the distance between the mean in that inflection point, well, it's going to be different for different populations for different metrics, but that distance is called one standard deviation. Do you guys see 7 integers below this bell curve from -3 to +3, right? That's called z-score, and a particular individual might have some z-score. Yesterday, I had you guys measure your height and your friend's heights, right? And then you figured out where you sort of landed in the big scheme of things. Let's suppose that you and your small group of friends are somehow representative of a large group of people. It's kind of a crazy assumption, but we're doing a simplified version of this, right? If you personally had a z-score that was 0, that means that you are exactly average in your friend group. If you have a z-score that's positive, that means you're tall among your friends. And if you had a z-score that's negative, that means you're short among your friends, right? You guys got that? Okay. It was probably somewhere between -3 and 3, because anything outside that is like a crazy statistical aberration, right? Okay. We were looking at the z table. Now the z table goes from here. There's the left half and the right half. Left half is negative z-scores. Right half is positive z-scores. So below average and above average. Oh, look, we're like shading in some part of the bell curve. You guys see that? And it goes from -3.49 to +3.49, and that will cover 99.98% of all the data. Okay, I see that? Because yeah, now do z-scores beyond 3.5 exist? Yeah, but it's like a like a 1 in 100,000 chance that you right. So it's like winning the lottery to have a z-score beyond 3.5 for any particular metric. Right. So here's what we do today. We're on stat C. This is the last page of this puzzle. Now, I have 2 stories lined up. There's a height story and there's a volume story, right? Which is similar to some stories you guys seen recently. Here's what we're going to do. We're just going to do one of these together and ignore the other one. If you want one more story for fun, then you got it. You can do it. But if you just want to ignore that and just turn in what we do in class, then that's fine. Okay. Because there's one last concept that I want to introduce to you guys, and that's if you start putting things in groups. So one more idea. And this is going to help. This is similar to what particle physicists do over at Large Hadron Collider over in Switzerland and France. And so what do you guys see next week when we get to quantum mechanics and particle physics is, suppose that scientists are smashing atoms together over this Large Hadron Collider, and they're saying like, hey, we discovered a new particle, we discovered a Higgs boson. But what does that really mean? Do they have a picture of it? Well, no, because it's too small to take a picture. What they're doing is they're colliding atoms together and they're getting statistical data about what happens from that collision. And based on that statistical data, they can aggregate lots and lots of smashed atoms. They say, oh, well, there must be a particle that has this mass and this charge and this spin property. Otherwise, we would not have seen this type of collision over like this many smashes. Right? All right, so let's head into this. What we got so far. Here's how to get the average. You guys have known that hopefully for years. Here's how standard deviation. We've been doing this for a few days. Here's z-score, which could take you to that z table and that probability curve, right, for an individual. All right, here's a new concept that I'm introducing right here today. What is the standard deviation for a whole group, right? And what you do is you take standard deviation for an individual and you divide by the square root of the group size, right? Right now, this will make sense when I go through this example, what that means and what its significance is, like why this matters. Right? Right. So suppose the average human height is right now. Here's where again everybody has different numbers, just like it's been all along. But your numbers should be kind of close to mine. Right? So I have this average height is 175 centimeters, and the standard deviation, like a plus minus factor, I'm calling 10 centimeters. Right. Now remember what that means. 175 centimeters plus or minus 10 centimeters should account for 68% of all humans, if my numbers are accurate, right? And you got some tall people and some short people, but about 2/3 of people should be plus or minus 10 centimeters from this average, right? All right, so first question, what is the expected value of the height of the next person who walks in through that door? Well, it could be anybody. So if you had to put money on the table, do you think you may as well just guess the average? That'd probably be a good guess as any, right? So go ahead and take that average, just copy paste it right here, right? And then 50% chance it'll be less than that, 50% chance it'll be more than that, or yeah, I mean, or some people might be exactly that height. Right? It's probably the most common height, right? Just whatever average. What's the standard deviation on that? Well, if it's just an individual person, that's just this number right here. So take this number, just copy paste it right here. Right? So it's like your plus or minus factor, right? Okay. Now, remember, last few days, we've been applying this here equation on a whole group of people to get that number. But let's say we've done past that, blah, blah, blah. We've already cut through that. And I'm just giving you that is the standard deviation for an individual, right? Okay. All right, moving on. Therefore, what is the percentage that the next person has a height that is greater than or equal to, like a tall person? And mine says 185 centimeters, right? Obtain a z-score and consult the z-table, right? So we need to get a z-score. Okay. That's this formula right here. So I will apply this for you guys in the notes. You might remember how to do this from the last couple of days. And if you do, then go ahead and you know what you're doing. Z-score is, I need the target individual, which for me is this many centimeters. Subtract the average, which is this number, centimeters. Remember, my numbers are different than your numbers, but probably kind of close-ish. And then, now, okay, so that's the difference. That's just a number difference, right? But remember, z-score is the count of the number of standard deviations. And the way you get that is to divide by the standard deviation. Your sort of plus or minus factor, right? Guess that? Okay. I wonder what the z-score is for my guy. Oh, I don't need a calculator for this. I can see it just, the top is 10, the bottom's 10. I have a z-score of exactly 1.0, which is kind of convenient, but that doesn't work out that way for everybody, but let's go. Okay, to the next step. All right, has everybody got their z-score for their person? Mine's exactly 1.00 on the dot, and yours is something, right? This one doesn't have to be an integer. This could be something crazy, okay? All right, you guys good? All right, now let's, so next question. What percentage of people would be that height or taller walking through the door? Now, since this is a particularly tall person with a positive z-score, do you think that there's a less than 50% chance that a super tall person walks through the door? That kind of makes sense. That would be the case, right? Right. Now, let's hold on to that idea. Flip over to the z-table. Right. So negative z-scores on the left. I'm pretty sure I gave everybody a tall person, so everybody should be on the right half of the table, which is this one right here, positive z-scores, right? So Z is, go down and find your z-score. Now I see 1.0 right here, right? And then you can get more granular. So if yours was like 1.05, for example, then you go over 1.00, 1.01, 1.02, 1.3, 1.04, 1.05. You guys see it across the top, so it's like, it gets more granular. You see that? Okay. Now, since mine is exactly 1.00, that means I care about this cell right here, okay? But yours might be anywhere in this table, okay? Now pause right here. Did you guys find where you are on this table based on your z-score? Okay. Who's having trouble finding your place on the table? Okay, so everybody's got it? Right? All right, so let me zoom in and see what number I got. Mine says 0.8413, so wouldn't it be like 84.13%? Okay, now I'm gonna round that a little bit. I'll just round that to 84%. Is that okay? 84%? Okay, which actually should look familiar because it happened to be one of the numbers we were working with yesterday, just for my particular example. So I'm gonna go to my stats part C, okay, and say, remember what that means, context, right? That means the shaded in part of the curve is 84%. Isn't that true? Right. But the question is framed, how many people are taller than that or equal to or taller? Wouldn't that be this white tail on the right side? Right. Because if the shaded in region is 84%, then what's this actual white tail on the right side? 16%. And that is the answer to the question. Right. Right. So now, obviously, everybody's numbers are different, but if I gave you kind of a tallish person, your number should definitely be less than 50%. Like mine's 16, that's less than 50%, right? Okay. Right. Pause right here. You guys good so far? Right. And actually, there's nothing really new so far because you guys could have done this based on what we've done so far, right? But there's a new concept that we're about to introduce right now. using same average height and standard deviation, blah, blah, blah. What about, what is the expected average height for a group of 5 people who walk in through the door? Okay, now we're looking at a group of people, right? So this is not, because an individual, you never know. It's kind of fluky with an individual. You could win the lottery and like, some 7'10" person could walk in through the door and it's like, oh, that's crazy, but could happen. Okay. Do you guys think that for a group of people, they probably have the same average height as for an individual? Same average? Do you think it's the same average? I think it's the same average, right? So this box and this box should also equal this box, right? Is that true? Right. Now, all right, now here's where things start to get different. What is the standard deviation for a group of 5 people? Here, let's do the formula first, and then I'll go back and explain why sort of this makes sense. You guys see this formula right here? You gotta take the individual standard deviation and divide by the square root of the group size. So I'm gonna take, mine was 10 centimeters. Oh, whoops, I forgot my unit up here. I just realized that, centimeters. Okay. I'm gonna take those 10 centimeters standard deviation, which is different for you, probably, right? And divide by the square root of 5 people. Right? Let's see what that comes out to. It's 10 on the root 5. Right? I'm looking at 4.47 centimeters. Right? Ooh, do you guys see that the standard deviation decreased? Right, from 10 to like 4.5. You see that? Okay. Now I want to tell you guys why it makes sense that it would decrease. Right? The larger the group size they have, if I got a whole group of 5 people walking into that door, right? Like, what's the chance that on average, all of them are super tall? Let's say like over 185 centimeters. That's where I'm going with this next question. Okay. Wouldn't it make sense that the larger the group size you have, their own average height of that entire group is going to sort of tend towards the mean, right? Right. Like for like if a single person walking through the door is like 7 foot tall, like, okay, well, that's a fluke, but it could happen 7 foot tall. I mean, there's some good people. But what if a group of 5 people walked in and they were all 7 foot tall? Wouldn't that be like, wow, that's a crazy statistical aberration? That'll be very unlikely to happen. Because the standard deviation is like decreasing, right? It's kind of like this bell curve is getting like squeezed in, right? And how about this? Let's take this to an extreme, which is another tool that we've been using throughout the year. What if the entire world of 7 billion people walks in through that door? 7 billion people walks in. Wouldn't the average height of 7 billion people have to also match exactly the average height of 7 billion people, right? And then what's the chance that like the average height would be more than that? Wouldn't that have to go to 0? Because the standard deviation would also be tending towards 0. Guys, if you take any standard deviation and divide by a square root of 7 billion, doesn't this number tend towards 0? Right? Because what's going on is that your bell curve is getting squeezed in, and the average for a group of 7 billion, well, there's only one possibility. So you have basically a spike at the average, and that's the only possible solution, right? Kind of makes sense? You see that? Okay. All right. So last couple questions here, and then I'll go back and fill in the rest of the story. Right. So for someone to walk in who's 185 centimeters tall, well, I know what that is for an individual. There's only a 16% chance. But what about a group of 5 people? What if on average that group of 5 people had a height of 185 centimeters? Now, I don't know the answer right away, but I'm going to guess that it's probably close to like 2%. You guys think there's probably, if it, for an individual, it's 16%. Do you think a group of 5 people is probably close to like 2% chance? Right. Well, let's find out. So I need a z-score for a group of 5. So this z for group is equal to, right? So my target value is still 185 centimeters, just like it was before. The average group size is, or the average height is still 175 centimeters, just like it was before. So far, this looks exactly like I did before. But now it's not 10 centimeters standard deviation, it's 10 over the root 5, which came out to like 4.47. Let's see what happened to the z-score. It is 2.24. Ooh, and remember that's a unitless number. That's centimeters over centimeters, right? That's getting to be a pretty big z-score, right? Right. Let's check. Okay. So we got a z-score. Go ahead and write that down.
What did we subtract?
Right. So you take the target height, which is right here. you're gonna subtract the average, which is, well, you see that average, which is that average, which is that average. It's the same number over and over. Okay? And then, remember z-score is a count of the number of standard deviations. So you're going to divide by your new standard deviation, which is this number right here. And that's the individual standard deviation divided by the square root of the group size. Okay? Right, so you guys good? Right. Okay. And now I'm getting a z-score that's significantly larger than it was for an individual. Right? Okay. Right. So here's what we do. We're going to answer this question, and then I'll go and tell you guys how this relates to quantum mechanics, and then then we'll wrap up the stats packet. Right, so we got a z-score of pretty big. I'll call it 2.24 is my number. So now I'm ready to flip over to the z table. I need to find this new z-score of 2.24, right? Here's 2.2, 2.20, 2.21, 2.22, 2.23, 2.24. That's this number right here. Okay, that's good. Now let me zoom in and see what I got. Okay, 98.75%. You guys see 98.75% versus just my numbers, right? But I bet yours is not too far off from that. Right? So I have 98.75%. Now, if the shaded part is 98.75% of the whole population, then how much is this white tail on the right side? Would it be the other 1.25%? Is it 1.25? Right? So let's flip back here to stat C. 1.25% chance. Remember I was estimating before we started plugging and chugging, I say, I'm going to guess about 2%. Okay, so I wasn't too far off, right? It was like 1%. I get it. How do you get what? Probably? Okay, yeah, here we go. All right, yeah, so you're going to take your z-score, right? So I have 2.24, okay? I'm going to flip over to the z table, find my z, 2.2, here's 2.2, and then 2.2, and then see it going across the top. Here's 0.04. So here's 2.24 right here. 2.24 is right there. Right? And if I zoom in on that number, it says 98.75%. Okay, did you find your own number? Okay. Your z-score is 1.48. Okay, so if you have 1.48, I'll go 1.4. Now 8's way over here. So your probability is, let's call that 93%. Okay. Now, remember what that means though. That means 93% are less than that. So therefore, what percent are greater than that? The other 7. Yeah. So that is the answer to your box. Is so where I have 1.25, you have 7. Okay. All right, you guys good? All right. And now compare these two boxes, because the new percentage should be much less than the old percentage. Right. That's also true, right? Right. Right. So here's sort of an analogy to quantum mechanics. Right. So there are a bunch of particle physicists over Large Hadron Collider. They're smashing atoms together. They can't take pictures of these subatomic particles or atoms, but they can do calculations and get mass, charge, and spin data that would indicate that ththese particles exist. And when they smash together lots and lots of atoms, it's kind of like grouping together lots of data, right? Now, what does that have to do like heights of people? Suppose, can you guys imagine that we are a bunch of aliens in a flying saucer flying around on Earth, over Earth? Can you guys imagine that? We're up in a flying saucer, we're looking down. We see there's lots of people walking around, and we see that they built these huge buildings, like these huge auditoriums and stadiums. Well, we can't see inside the auditoriums. And we're speculating. We say, you know what? I hypothesize that there is such a thing as a sport called basketball, right? And we sort of figure out, okay, well, I think it's probably teams of 5 versus 5. And I think how it works is like there's these rings. You got to take this ball and get it into the ring, and it's up at some height, right? And we pretty much kind of know that basketball exists, even though we can't directly see it inside these auditoriums because they're covered, right? Right. And we know that if this is true, if this is really true, then it would create an environmental condition where it would be advantageous to be really tall. And if you were really tall, you'd probably be highly correlated with being good at this particular sport. that we think exists to blah, blah, blah by these rules, right? Also, furthermore, it would make sense that there would be groups of 5 very tall people walking around, and that would be like a basketball team, right? This is sort of like trying to figure out, does the Higgs boson exist, right? Except we're looking for like mass, charge, and spin properties, except now we're aliens in a spaceship looking around on Earth, right? And so for 5 people to walk through the door, that would be crazy tall, let's say like about 7 feet tall. Well, individuals walking through a door 7 feet tall, yeah, we see those. I mean, they're kind of rare, but we see them, right? But if there was a group of 5 people that were super tall walking around all together, especially if there were lots of groups of people that were 5 or 7 foot tall all the time, right? You would never really expect to see that randomly, or maybe like once ever. It'd be like winning the lottery. That 5 people would walk through the door that were all 7 foot tall, right? But if that regularly happened, that would be a pretty good experimental indication that basketball teams exist and therefore the sport basketball exists, right? You guys trying to get that? Right. So if this happened and this was like, if this happened instead of 1% of the time, if this happened like 20% of the time, like, whoa, there's something weird going on. There's some phenomenon happening so that lots of tall people are walking together. Okay, you guys get that? Okay. Tell you guys what, if I got one more example here that's on volume of water. You guys remember like volume of water in a bottle, right? We're not going to do this. You don't have to do it. If this stat's really intriguing, you're like, whoa, I see like what kind of power this really opens up to be able to crunch numbers. You have one more that you can do for fun, but you don't have to. Right? If you feel really good about your whole stats packet, then go ahead and pop this a great tray. I'll get you guys some points. If you have some parts missing and you want to turn this in on Monday, that's perfectly fine. You can turn it in on Monday. Okay. So here's what I do. How much time we got here? We got until 24. Oh, okay. Well, we got some time. Right. So the rest of class, I will hand you out these quarter pages. Next week, we're going to put together these quantum journals. So you should have a bunch of paper on your desk. Are those staplers still going around? Right. So staple together 4 pieces of paper and see what I did here, right here. And tell you what, if you don't want to handwrite it out, I did upload a copy of this to Google Classroom. If you just want to print it out, that's perfectly fine too. Right. And then we're going to spend next week. And I'll just tell you a little bit of each one, keep some notes, draw some diagrams. And yeah, you guys get to learn about quantum mechanics. All right, we'll call that a do.